Okay, I think a majority of the people are in here. So maybe let's get started with the second session of the day. Hi, everyone. Thank you all for coming back from your coffee break. I will try to get you guys out in time for lunch. So our first speaker is Robin Jia from USC. He got his PhD, I think, in 2020, right, from Percy's group at Stanford. And he's done a lot of work in natural language processing. So I guess we'll hear about some of this today. Please join me in welcoming Robin.
Awesome, yeah. Yeah, thank you very much. So just kind of like a preface, yeah, I think this is going to be a very different kind of talk than the first two talks of the day. So I'm, my research is all in natural language processing. I think it's much more on the empirical side, but over the years I've really benefited a lot from talking to folks who are like more theoretically minded, more in the kind of like core machine learning community, such as folks from Percy's group, and also some of my collaborators who are here in the audience today. And so this talk is kind of my attempt to take a lot of lessons that I've learned from the more empirical side of studying distribution shift and trying to distill that into what I think are some like interesting questions that maybe folks in this room maybe might find interesting to think about. Okay, so my starting point in trying to think about distribution shift and all these sort of related topics is really like I'm interested in this question of like, why do these models break, right? And so this was relevant, when I kind of started this sort of research in 2017. It's maybe even more relevant today, where you have these large language models, and they're surprisingly good at a lot of situations, but they also make a lot of these mistakes, right? So they might hallucinate things. They might introduce insecure code if you're using them to write code. And so I think a really important thing to ask is like, what are these sorts of kind of meaningful failure cases, and how can we explain and anticipate them? So we started to think about that. I think that there's kind of a few like natural explanations that you might reach for. So one of them is this idea of distribution shift. And sort of in the classical sense, we're probably going to think about distribution shift that happens at the fine-tuning stage for language models, right? So some sort of pre-training happens with language models, but then they're fine-tuned generally to respond to user questions, to follow instructions or something. And you can easily imagine that there would be some distribution shift there, right? And this seems to best match kind of the classical notion of there's some train set, test set is not IAD with respect to the train, and you might encounter issues because of this. But there's kind of a couple other, I think, important characters in this story if we're trying to understand language models. And the first one has to do with pre-training, right? And I'm going to use kind of in quotes distribution shift from pre-training to represent this idea that like certain things are kind of common in pre-training data and other things are underrepresented. And this I think also has like a really great explanatory power when we're talking about the sort of model failure cases. And then finally, there's like a third thing that I think is kind of like hard to really formalize, but I think there's a lot of intuition that we've built around it that is actually very powerful too. And that's just this idea that like certain examples are just intrinsically difficult. So this is like some random IMO geometry problem diagram, right? That I think we often want to say something like there are certain examples that are just hard in a way that has nothing to do with the training distribution at all. They're just harder. Okay, and so in this talk, I'm gonna, like I said, kind of present a lot of this sort of empirical research I've done in NLP from 2017 to the present day. And yeah, I'm gonna try to, since I'm here at Simons as a bit of an outsider, I'm gonna try to take these observations and distill them into some interesting questions that you all might be able to analyze. Okay, so the organization of this talk. So I first want to just, let's kind of set pre-training aside for the moment. I want to talk about this balance between, do we explain failures in terms of distribution shifts, or do we try to explain things in terms of example difficulty? And so I'm going to start with, actually, this is like the kind of the very first work I did back in my PhD along these lines. So it was 2017, so deep learning was just kind of like taking hold in the natural language processing world. And in particular, there were these question answering systems, right? So they could like take in a question in a paragraph and extract the answer to the question from the paragraph. And they seem to be doing very well at this. But we really believe that they weren't really kind of doing question answering. They didn't really understand how to do language. And so we designed this test to kind of expose how brittle these models were. So the idea of the test is simply that we add an additional sentence. So that's the sentence in red here. And the sentence is kind of carefully designed so that it almost answers the question, right? So what changes that, like, the question asks about some like Huguenot colonists, and we added a sentence about some other group of colonists. And this is basically able to trick the model into giving the wrong answer. And so we showed that, there's a lot of these fine-tuned question answering models, including things based on, pre-trained models such as BERT. And they generally just get a lot worse when you add these distracting sentences to the input. Okay. So, the question now is like, well, why does this happen? And I think that there's at least one sort of very natural explanation that what's happening is basically caused by distribution shift. So one sort of explanation you could try to give is that these examples are not necessarily fundamentally that difficult. It's just that they happen to be sort of not well covered in the training data. And in fact, that we had some evidence for this. So here's kind of a simple experiment that we did. On the left part of this graph is just what happens when you train on sort of the standard question answering training data. And on the right, we basically took this sort of like pipeline we had for generating these distracting sentences, and we also applied it to the training data, right? So we basically did some data augmentation. And when you do that, your accuracy on the adversarial test set goes way up, right? So this just suggests that, like, well, okay, if you just had a different training distribution, if you eliminated the sort of gap in distributions, the model itself is actually capable of learning this quite easily. On the other hand, the model still fails to generalize in some broader sense. So that's the third kind of gray bars are showing that if you just modify the way you generate the distractor sentences, the model's still not that good, right? So this is I think how I was at least thinking a lot about these sorts of issues. It was just, oh, these models are really overfitting to the training distribution, and they're not able to learn the right thing that generalizes. Okay, so this is certainly one view you could take. If we fast forward now to 2023, so this is not my own work, but this is just some other papers. There's been other work showing that these same sorts of distracting sentences also fool like large language models. So this is like some experiments on like GPT-3 showing that, yeah, you can like give it a math problem, and then you can add some sentence that like introduces some irrelevant facts about the math problem, but they kind of seem like they might be relevant. And this, again, like distracts the model into giving the wrong answer. Okay, so when I start seeing like other cases where essentially this same sort of attack also works, these models, I start wondering, like, so like, why does this attack work? So, I mean, you could still try to stick with this argument that like, oh, probably the fine-tuning distribution for this model also didn't have these sorts of data and so forth. But like, I don't know, I think I start to wonder that like maybe this is not capturing the full picture, right? Because probably this model was trained on like some completely different distribution from the model in the previous slide. Sorry, yes.
I'm so surprised by what you're trying to discuss here. You have a case where someone. Sorry, quickly. So why is this surprising? You're calling it distracting. As you said yourself, you could call it adversarial. So you could actually modify adversarially the context. So why is it surprising that the model would be misled? You're calling it distracting instead of adversarial. These are like playing with words, or is it something very crucial here?
That's so the distracting versus adversarial is kind of just I guess maybe a slip of terminology. I think in the original paper we referred to this as adversarial, although I think currently I would refer to it probably more as distracting. I actually had a slide that I took out about how adversarial means very different things in different contexts, and it's kind of confusing. In terms of why is this surprising, I don't know if this is necessarily surprising, but I still want to be able to explain why it happens, I suppose. Yeah. Okay. So right. So we're saying that like this kind of repeated this sort of pattern recurs again and again. Sorry. Like related to this, like I guess I want to just like have an aside, which is I'm sure something that people here are generally aware of, but I think is helpful to remember is that, like, distribution shifts are not necessarily harmful, right? And so I think that the case I like to think about, which is something I've worked on a little bit, is, like if you're thinking about active learning, right? So what's the intuition for active learning? Like, you have some sort of nice data set like this. The examples you want to sample are the things that are close to the decision boundary, right? And if you can sample these things on the decision boundary and learn these well, you kind of generalize to the easier things, like, kind of for free, right? And by the way, the reverse is not true, right? Like, if you sampled all the other stuff, you don't necessarily learn the exact right decision boundary. And so I think what this kind of just like very simple parable tells you is that, like, the effective distribution shift, to kind of predict whether the distribution shift is going to challenge the model, we also have to think about some notion of example difficulty, right? In this case, it's like closeness to the decision boundary. But more generally, like, what could this refer to? And sort of one idea that actually, like, one of my colleagues has done some recent work on, thinks about this concept of sensitivity, right? So they basically show that transformers generally prefer to learn these sort of low sensitivity functions. What we mean by that is functions where, for example, when you change one bit, if the input is a Boolean vector, the value of the function doesn't change very often. Or in generally, right, if a small part of the input is changed, like the function does not change very often. And so if you believe that this is just kind of an intrinsic bias of the architecture now, this should lead you to think that transformers generally are just going to struggle when the actual function you need to learn is higher sensitivity. And I think this sort of intuition actually kind of underlies a lot of things that, in retrospect, a lot of things that I and others have worked on, right? So this sort of sensitivity-based explanation to what's happening in this example is that the model sort of is not dumb. It correctly knows that if this distracting sentence had these two words changed, right? If it actually said like "you Huguenot," then this would answer the question well, right? And basically, the model is like not sensitive enough to the change of these two keywords, right? So this is no longer like appealing necessarily to the training distribution. This is saying that there's like something about this example that's actually hard, at least for this type of model. And I think this sort of intuition really does hold water because, in fact, like in some of my other work, we've used it to generate hard examples in like non-IID setting, or in IID settings, right, as opposed to this sort of distribution shift setting from before. There's a couple of examples. So like we created this data set called Squad 2.0, where we basically tried to make it hard by creating these questions that were kind of like almost answerable, but they were very similar to answerable questions, but just very slightly different, right? So like changing the word opening to closing, asking about closing speakers, and the paragraph talks about opening speakers. And another thing I worked on was this framework that again we called adversarial data collection. But you can ignore the term adversarial if you want, on this platform called Dynabench. So Dynabench, the idea of Dynabench is just that you ask people to interact with a model in the loop, and basically they are going to try to write examples that they think are hard. And when you do this, you wind up finding a lot of examples that seem kind of actually very related to this sort of like sensitivity phenomena. So for example, this is just a figure I had sort of lying around, but I think the example here makes the point. You might have a passage that says like pit bulls can make great companions. And well, if you tell a model, well, if you basically ask a model, does this paragraph imply that bulls can make great companions? It will be very confident in saying yes. And again, here, right, this is like, what is this? This is like a very, very near distractor, because if you just had another word in front of bulls, then this would be entailed by the paragraph. Okay. So all this is to say, like, I think like this intuition about like sensitivity and the models like having this low sensitivity bias is actually like, it clearly has a lot of explanatory power, just to understand model failures in general. One slide I want to mention is, so you might be wondering, like, what about things like adversarial perturbation? So there's also cases where we might see models be overly sensitive to small perturbations. This is also something that I'd worked on in the past. For example, like you just like try to find some like synonym substitutions that cause a model to give a wrong prediction. My argument here is basically just like that, like, models are actually pretty robust in the average case to these sorts of perturbations. And this is really kind of like an entirely different ballgame that I'm not even going to really talk more about in this talk, right? But this ballgame is basically saying like, well, we want the model to be 100% accurate in some neighborhood. And if it's less than 100% accurate, then there's an attack that succeeds. And yeah, essentially, this is just kind of a very different, it's a much higher bar for the models, whereas I think for this sort of lower sensitivity stuff, low sensitivity bias issues, it's just like kind of much more readily apparent that the models really do struggle there. Okay, so I think the summary so far, what I want to say is that, like, I think this sort of like thinking in terms of distribution shifts, I think it's a useful way of explaining away some sorts of failures, but this is only a partial explanation, right? Because we also have to explain basically why is this particular distribution shift challenging, and this basically leads us into also having to think about example difficulty. And I think what's hard here is that whatever intuitions we have, I think are generally quite harder to formalize, but I think they're actually, the evidence suggests that these actually are real. For example, they help us just anticipate what sort of data sets will be hard in general. Okay, so this is kind of these two characters that I talked about, these fine-tuning distribution shifts and example difficulty. And I now want to talk about sort of where I think kind of pre-training factors into this picture, right? So what is the role of now the pre-training distribution? What are the possible shifts here? Okay, so I want to talk about maybe what people think about when you think about distribution shifts, and that is like generalizing across domains. So this is, I tried to get like a classic example here. So it's actually from like John Blitzer and Hal Dome's like tutorial in 2010. So here's like a very classic domain adaptation problem. You have some training data that's like looking at Amazon reviews, and it talks about like books. And you have some test domain that is also Amazon reviews, but it talks about like kitchen appliances, right? What I want to argue is that this is like, if in the absence of other sort of knowledge, this is actually like an extremely hard problem, right? So at test time, you're going to get these like very new like negative sentiment phrases, right? So here, like this person calls this, this deep fryer defective, right? But like people are not going around calling books defective, right? This is like, it's not something that you would really even hope to learn from the training domain. Right, and it get harder, right? There's another example adapted from their tutorial, right? That like some words like are positive in one domain, right? Like a vacuum being loud is pretty bad. Like a speaker being loud is pretty good. And so like there's a lot of these like actually really hard just like extrapolation challenges associated with this sort of domain generalization, right? The saving grace here is that we don't only have the training data or test domain alone. What's really been happening in the empirical world is that like we need some other knowledge besides what we can get out of these two domains, and this comes from pre-training generally, right? And one way to think of this, to put this in the context of this sort of distribution shift lingo, is that even if you're trying to generalize to some test domain that's out of distribution relative to what you fine-tuned on, it's in some sense in distribution of pre-training, right? Because like speakers were probably talked about in your pre-training corpus and so forth. Okay, so just like a couple of examples of why this has sort of been beaten into me. I actually co-organized this shared task in 2019 on generalization in question answering. And we were really kind of trying to get the community there to think about this exact question of like, how do you create NLP systems that generalize across different domains? And so the way the shared task works is that we got a total of like 18 different basically data sets, right? Which came from Drew had examples from a bunch of different data sources. And we basically said, here's 6 of them that you can use for training. There's other 6 that you can use for development. And we're going to have 6 more that we're going to hide from all the participants until the very end when we do evaluation. And that's going to be how we test if people have really figured out how to create generalizable models. And so we ran this experiment. We ran the shared task. We got like a good number of participants. And what happened in the end what happened in the end is that like the number one thing that people could do to make their models better was to replace BERT, which was kind of like the standard when we had first released this, with some other pre-trained model that was better. So something like XLNet at the time. And there are a lot of other sort of like fancier things that were tried, and they generally like didn't work nearly as well as just like have a better pre-trained model. And in particular, like some of the places where this approach really shined was when you had test data where we were asking questions about types of documents that were never seen during fine-tuning. So things like we had a hidden test data set that came from like transcripts of speeches, which is actually quite different from like a news article or something. You have all these disfluencies. People, it's not nearly organized in the same way as like as a normal article would be. The models generalized, they're just fine. And even things like PubMed abstracts or something, the models generalized very well. So this is one example of just saying that, like, yeah, pre-training for this sort of shift, pre-training is just very powerful. Okay, we had another study. So this was a study I did with one of my students, Bill, and his co-advisor, Jesse Thomason. So we were interested in understanding these sort of like vision language systems and how different types of those systems generalize. And so we had like a few different ways to evaluate this. So one is kind of similar to the stuff I showed you in the first part. So we could evaluate them on things where we can change a question slightly. For example, changing the phrase at least 2 to less than 2. So this is like a small change that induces a change in the label. And it's basically trying to exploit the fact that models are bad in cases where you need high sensitivity. And so here, as you might predict from the first part of the talk, an end-to-end pre-trained model does not do so well. And in fact, like there's the other big question in this paper was like, could you do better in various situations if you had some neurosymbolic pipeline? In this case, yes, a kind of completely different architecture does better. On the other hand, we also looked at things like dataset shift. So here we trained on one dataset, GQA. So this is a dataset where they took some images annotated with scene graphs and crafted these really sort of complex compositional questions based on that. And then we evaluated on VQA, which is a data set in the same format, but the questions are like written by people. And so in some ways they're simpler. Like they're not like as long as the GQA questions, but they require some other sorts of knowledge, right? So here this question is saying, can you park here? And there's a picture of a fire hydrant. And so you're supposed to say no. And so in these sorts of situations, like, some sort of like neurosymbolic pipeline is actually like not going to do well because it doesn't have the knowledge to answer these sorts of questions. But in this sort of shift, right, this sort of information is in distribution in terms of pre-training, and so the end-to-end pre-trained model just kind of like succeeds here. Okay, so all these examples are just to argue that, like, if you have something that is sort of covered well in your pre-training distribution, you're like likely to be able to generalize even despite some sort of fine-tuning mismatch with the test data. Another paper we had that I think kind of tries to delve further into this is this paper about what we called likelihood splits. So the idea here is that we're going to create some train test splits. So this is like kind of splitting your fine-tuning and your test data, but in a way that's actually based on the pre-trained model. So here's the idea. We're gonna, you have a big data set. You can, run a language model on each example in the data set and just basically ask it like, how likely does this example seem, just in general in terms of the text. So you're not using the label here at all. And you get some distribution. There's some things that are sort of like seem more implausible, let's say, to the language model. And we can take those sort of long-tailed examples and reserve those as our test set and fine-tune our model just on the remainder, right? So we basically fine-tune on the head of the distribution and we test on the tail. And as you might expect, kind of intuitively, this is actually much more challenging than an IID split, right? And so this is kind of argument was like, this might be a good way to just like kind of create some distribution shift that actually tests your model, and you don't necessarily have to do anything domain specific. You just need to be able to run a language model. Okay, so I think an interesting question though is that what happens if you reverse this? So you can call these reverse likelihood splits. So now what we're going to do is we're going to actually train on the sort of tail of the distribution and test on the head of the distribution. And so in some sense, like the mismatch between train and test is exactly as big, right? As was before. But now this is actually easier than IID, right? And so this basically shows you it's not just the fact that the fine tuning and test data sets are different that's really causing the problem. What's causing the problem is that you're trying to generalize to things that are in the long tail, and those are hard. Generalizing to the head is kind of easier because, yeah, presumably because those things are already very well covered in the pre-training data, right? So what you could say is that what really matters here is a shift relative to what was in the pre-training data. And this is kind of, I think, a pattern that's coming up again and again as I do sort of try to use language models in my own research, that this issue of like how rare things are during pre-training like really matters a lot. So this is one anecdotal case. Again, I don't think this is like surprising necessarily.
Hey, Robin,
but,
I have a quick question about
yes.
So how do you get the low likelihood? Is it essentially low likelihood here just means the things that would not, the things that you do bad on, the things that you have less confidence on?
No, so we're only looking at the X's here. So you just look at the,
I know,
yeah.
But I'm saying, how are you scoring the likelihood?
How am I scoring the likelihood?
How are you scoring the likelihood that you, I mean, whatever you're calling long tail, or what is that? How are you scoring that?
So it's, we just, in these cases, in all the tasks, the input itself is just like some sort of like sentence or paragraph. And we're just looking at the like language model's ability to predict the next word in those paragraphs. But the task is separate. The task is like you're classifying that paragraph or something.
Okay, so it's the things that you're likely to actually predict wrong on, right?
No, well, because okay. So maybe I can just give a concrete example. So like one example is just there's a data set called Spider, which basically is like you get like a natural language question, something like, I don't know, how many cars were manufactured in 2011 or something. And you have to convert that into a SQL query because you have some database about car manufacturing. And so, yeah, so the actual task is like convert natural language to SQL. But to get these likelihoods, all we do is we just look at that query, like how many cars were manufactured in 2011. And we just ask like, how likely is that sentence like to appear in your pre-training corpus? Because that's what the language models measure.
Not fully, but
okay. Yes.
I think maybe the question here is this one wondering about this. Like this is probability. You say log likelihood, but it's log likelihood under a particular model.
Yes.
Right. So I guess what's the relationship with that model and the model that you use for the actual the actual prediction that you do?
Yeah. So that's a good question. So we had a couple of scenarios. We tested a couple of different things. So you could just so one possibility is you could just take a pre-trained language model and first extract these log likelihoods. And then you could take that same model and fine tune it on your, on your labels. And that could be the model you're evaluating. But you could also have a different language model being used for the log likelihood estimation and for the kind of the actual task. And the results you get are very similar. Yes.
So I was wondering about like the low versus high sensitivity aspect that you were talking about. There is like the words and then there is the representation, right? Like so ideally, like I'm trying to think about like if the sensitivity measured like in terms of like words versus like in the representation, because ideally you can have two sentences that are essentially the exact same thing with words being very different with one of the examples that you showed versus two sentences that essentially look the same except one word being different but completely changes the meaning. How is like is both of them considered kind of like the similar way the sensitivity is measured? I'm trying to kind of understand where the sensitivity is measured.
Yeah, I think that's a great question, and that's honestly one of the questions that I don't have a great answer for, because I don't think anyone has really successfully like formalized this for NLP. Like, what should that mean? Like, I suppose I would say that like if you could show that like just looking at the raw token sequence helped you predict the model's behavior, I think that would be really powerful, because then it's easier to just look at the raw token sequence. Probably if you look at things about the representation, you're going to get something that is more predictive of the downstream model behavior. But the downside then is that it's not a kind of a complete explanation, and that you have to explain why the representations are that way. So yeah, I think this actually relates to one of the sort of like future questions that I want to talk about. Yeah, how should we define that?
Yes. Maybe in the interest of time, we let the speaker finish his talk. You have like 8 minutes.
Okay. Yes.
And we'll take questions at the end. Sorry.
Yeah. No worries. Okay. Let's see. Right. So I was just saying that basically, like, there's just one case that we've happened to be working on very recently, is trying to get language models to generate these sorts of like things in this query language called CodeQL. Basically, this is a collaboration with some like programming languages people who, in that community, they've developed this particular language that's useful for like identifying security related issues in code bases. Okay. All you have to really need to know is that this is something that's like very long tail. Like, very few people actually are good at writing CodeQL queries. There's a very small amount of data. LLMs struggle on this. And we have tried really to like fine tune the models to get them to do this sort of thing better. And it's just really hard to overcome the kind of fact that these things were really underrepresented at pre-training time. In terms of like why that happens, right? This goes back to the question about representations. Yeah, I do think like kind of representation, understanding the pre-trained representations has to be a big part of explaining why why the pre-training distribution matters so much. Here's just kind of again one example of a recent paper we did with some folks in this room, Qingyi, Duqing, and Vatzel. So here we kind of just analyzed how language models do addition after they're and at least most of the experiments here focus on fine-tuning. So you have a pre-trained model, you fine-tune it on this particular task, which is just like add two integers together, and it turns out it can do this very well. And it learns this kind of very interesting mechanism where it kind of like tries to, some parts of it basically try to approximate the magnitude of the answer. Other parts of it are doing classification modulo some small number. So for example, like there's components that try to just like predict whether the answer is even or odd or something like that, right? And so if you can approximate the answer, the answer like mod 2 or mod 5 or something, you can put that together and get the right answer, right? So that's what these models seem to be doing. So you can ask, so how does it learn to do this? And pre-training is very important to this mechanism. So one thing we showed in the paper is that if you visualize the kind of word vectors corresponding to the integers, they already have, and after pre-training, they have some of these like very noticeable kind of like spikes in the Fourier domain that correspond to some like very familiar small numbers like 2, 5, and 10, right? So basically, like there's like a strong component in just the way that integers are represented in the model that has a periodicity of 2 or a periodicity of 5. And furthermore, like if all you have is that, basically all you have is these word vectors that say that that have these sorts of high period features, that actually is sufficient to make fine-tuning a lot better. So if you fine-tune a randomly initialized transformer, you get this black line, which basically doesn't learn very well as you train for longer and longer. And in particular, it makes a lot of off by 1 errors. It basically shows that like it can't actually compute the answer mod 2. But like once you just add in these pre-trained token embeddings, or like word vectors essentially, that sort of gives you, fine-tuning is able to do the rest. It's able to actually like take that information and actually like learn these learn this sort of much more robust mechanism. Okay, so just to wrap up this section, right? So the kind of key summary, and I think in my head is that like pre-training it's really interesting because it alters what is difficult for the model, right? So for example, all this domain generalization stuff becomes much easier if you get pre-trained representations. And they can help you learn successful algorithms at fine-tuning time. And we talked about this idea that, like, shifts relative to pre-training, the pre-training distribution, are actually what is posing a lot of challenges. Okay, so in the last 5 minutes, I want to talk about my sort of thoughts on what are some sort of interesting questions that you could try to ask about all this stuff I've been talking about. So one thing that is not very well defined in what I was saying is how really should we think of this pre-training distribution shift, right? So in other words, when should we say that a test data set is quote unquote matched with the pre-training data? And I think what I would say is that the obvious answer maybe is just to think about oh, what is the likelihood of the test data occurring at pre-training time? And I actually don't think that's the right notion. Because you could have something that doesn't, some test data that doesn't ever occur at pre-training time, but there's sort of enough relevant stuff at pre-training that it still kind of helps your model do well, right? And so I think this really requires us to think about things like, representation learning, right? So what sort of data is sufficient to learn the right representations that then can be leveraged by fine-tuning? Or maybe, thinking instead in terms of skills, which I think is something that people have increasingly been talking about in the context of language models. This notion that pre-training learns not only representations, but actually kind of entire abilities or skills. And when you fine-tune, really what's happening is that you're just the model is kind of selecting which skills should be used in this particular scenario, right? So some people might refer to this as the superficial alignment hypothesis, that fine-tuning actually does very little on top of pre-training. I think with these sorts of with kind of attempts to define this, we can start thinking about more about these what can we expect from interactions between pre-training and fine-tuning. So for example, can we kind of in some more abstract way analyze when does low frequency during pre-training time imply poor performance, even if you have matched fine-tuning and test data, right? So this is saying something like, without learning the right skills during pre-training, it's really hard to fix it at fine-tuning time, right? Is there a model in which we can kind of see this phenomenon emerge? And then the converse, I think, is also very interesting, right? So when can, if something is sufficiently frequent during pre-training, how does that compensate for distribution shift at fine-tuning time, right? So the intuition here is that pre-training learns some sort of skills that are very domain general, and fine-tuning, even on a training set that's mismatched from the test set, activates these domain general skills, and therefore it should still generalize to the test distribution, right? So in what settings does this happen? I think some complications are that, first of all, we don't actually know the data sets for pre-training or fine-tuning. We have some rough sense maybe, but for the frontier models, we don't really know. And I think another interesting complicating factor here is that I've been talking about pre-training and fine-tuning as if they're two entirely different things, but they're not entirely different. I mean, in some sense, they're really, the distinction is really a matter of scale, right? So if you do enough fine-tuning, it starts looking more and more like pre-training. Okay. Cool. Yeah. So I think, trying to formalize this is super interesting. There's two more thoughts. Yeah. On the notion of example difficulty and sensitivity, right? So yeah, like we talked about. So there's of course probably much more we could do to kind of define, formalize this notion of sensitivity as it relates to language. And I think there's also just more generally, I'm also curious, just what other principles are there for thinking about what things are kind of inherently difficult, maybe to a model, right? And this is tricky because, as we talked about, pre-training can change what is difficult, and also that things models find difficult are not necessarily what humans find difficult, right? So we can think about maybe things for the architecture, things related to pre-training, and of course, if we start talking about things that are difficult for pre-training, it depends on what data you're pre-training on. And so maybe the meta question here is how generally is it even possible to claim that a data, an example or data set or data distribution is intrinsically difficult? I'm not even sure if that makes sense in general. Like maybe that makes sense if you're talking about a particular architecture or something. And then the very last idea is just, we talked a lot about issues of like pre-training rarity. But I think there's also like a really tricky thing that we need to disentangle, which is that sometimes things are rare because they are hard, right? So here's like an attempt to draw a DAG here, right? So we talked about how the model is worse at things that are underrepresented in the pre-training data, but that could, why is it underrepresented? It could be that there are certain things that are hard. So for example, fewer people know how to do it, like write code QL queries. And therefore, those things would appear less on the internet, right? So hardness could be contributing to rarity. It could have this indirect effect. And of course, hardness also has this direct effect where it's just hard, so the model struggles with it. And so I think it would be interesting to try to disentangle these sorts of things. And again, there's this complicating factor of like, so we could try to intervene on like the rarity node at pre-training time, but how do we intervene, right? How would we actually? This goes back to this question of like, how do we know what data is actually helping the model learn the representations that matter for these sorts of examples? Okay, so anyways, I think hopefully these are some kind of like interesting thoughts, and related to distribution shift. And so I just want to end here and kind of put these little emojis signifying that I think there's a lot more to think about when it comes to shifts from pre-training and rarity of pre-training, how that affects models, and how do we define or attempt to measure what things are kind of hard in some data independent way. So yeah, welcome more questions or comments or ideas.
Thank you, Robin. Maybe we'll take one question while our next speaker sets up.
Yeah, so you mentioned there's paper that, for example, transformers prefer low sensitivity functions. Did they have a metric of what sensitivity means in that work?
Bata, would you like to answer this?
Yeah, there's a notion of sensitivity. Like it's an analog of the Boolean function. So you swap any of the tokens with a uniformly random token from some distribution, and then you see if the output changes. What's the probability of the output?
Okay, so the tokens here, are you looking at the representations in a continuous space or just like literally the tokens?
Yeah, so that's a good question. So I think for things like language, I think it makes more sense to for things like images, you can like do perturbations in the original space. But I think like, it's an interesting question to actually define this neighborhood in a rigorous way.
Okay, in the interest of getting out on time, let's move on to our second speaker of the session. We're happy to have Irene Chen. She is jointly appointed, I think, at Berkeley here and at UCSF.
Yeah,
right?
I have a bunch of affiliations that you can read on the slide.
Yeah. She's done a lot of work on machine learning and healthcare. And so we're very happy to hear what she has to say today. Please take it away.
Hello, everyone. Super excited to be here. This is my first time at Simon, so